Okay, let's jump right into this explainer. If you're building software today, you're probably totally swamped by all the AI noise, right? The hype, the magic bullet promises. It's a lot. But today, we're completely tuning that out. We're going to look at exactly how large language models work under the hood, focusing strictly on the core concepts from Chapter 1 of the Developer's Guide to AI. Because honestly, understanding these fundamental mechanics is the absolute difference between just blindly bolting a tool onto your app and actually engineering with it. So we're filtering out the magic, we're bringing in the engineering reality, and we're getting you that solid foundation.
Here is our roadmap for today. First, demystifying large language models. Then, the BERT breakthrough. After that, inference versus traditional programming. Solving problems with LLMs, understanding model limitations, and finally, plugging LLMs into code.
Section 1. Demystifying large language models. What exactly are they?
So the really crucial thing to grasp right off the bat is that these models are not programmed with rigid grammar rules. Traditional software relies on exact instructions, right? Think of a spell checker looking for a dictionary match, or a parser demanding perfect syntax. LLMs just do not work that way. Instead, they develop this inherent understanding of language by processing massive, and I mean unimaginable amounts of text. Think about how a toddler actually learns to talk. You don't sit a 2-year-old down with a textbook on verb conjugations. They just listen. They listen to thousands of conversations, absorbing context until the rules of language become totally intuitive. They learn how concepts connect purely through recognizing patterns over time. Well, LLMs learn in a remarkably similar way. They use deep neural networks to build mathematical connections based entirely on the patterns they see in their training data.
And that brings us to the actual fuel for our AI engine. To get a system to intuitively understand language like a human, you need data, a ridiculous amount of it. We are not just talking about reading a few encyclopedias here, we're talking about petabytes of raw data. To put that into perspective, a single petabyte is roughly equal to millions of human lifetimes of reading. Researchers realize that if you ingest this sheer scale of public internet data, web pages, millions of books, articles, code repos, these systems can accumulate incredibly deep knowledge. By churning through this massive library, the models literally map out the relationships between concepts across almost every domain of human knowledge. And that's how they eventually start demonstrating what looks, to us, an awful lot like logical reasoning.
Section 2. The BERT breakthrough. How Google revolutionized NLP.
To really get modern AI, we have to talk about a massive milestone from Google called BERT. Before BERT came along, early natural language processing models were practically terrible at understanding complex sentences. They read text strictly left to right, which means they'd totally lose the context of how words at the end of a sentence might change the meaning of the words at the beginning. To fix this, researchers introduced a radically new training method. Think of it like a giant automated game of Mad Libs. They started masking, or hiding, random words in a sentence and forced the model to guess the blank by looking at the context before and after the hidden word. Then, they took it a step further by swapping the order of entire sentences, forcing the model to guess the logical conversational sequence. By running these exact steps billions of times, BERT fundamentally learned to pay attention to the entire context of a text all at once. That specific breakthrough? That's what drove the massive NLP advances that led straight to the LLMs we're using right now.
Section 3. Inference versus traditional programming. The paradigm shift.
Okay, this right here is the major aha moment for any developer stepping into this space. Traditional programming is deterministic. You give it specific inputs, it follows exact if-then rules, and it does exactly what it's programmed to do, every single time. But AI models operate through a process called inference, which is probabilistic. When you give them new data, like your prompt, they aren't running an algorithm of strict rules. They're using what they've learned to infer a response by predicting the next most likely sequence of tokens. And a token is essentially just a chunk of data. As a dev, you really need to know that the AI doesn't see words, it sees tokens. Think of them like syllables or fragments. The word hamburger might be chopped into 3 separate tokens. So by calculating the mathematical probability of which token should come next, the model can actually generalize and react to brand new input it has literally never seen before. That's a level of flexibility deterministic code could absolutely never achieve.
Because these outputs are entirely probabilistic, the whole way we interact with these systems fundamentally changes. We have to carefully instruct the model with our prompts to restrict its potential responses and avoid hallucinated mistakes. You're not writing code here, you are literally trying to steer a statistical engine toward the right sequence of tokens. If you throw a vague prompt at it, the mathematical probability distribution of possible answers is incredibly wide and flat. It might guess right, or it might just veer off into total nonsense. It's a classic rule of computing, right? Garbage in, garbage out. By writing highly specific prompts, giving good context, and setting clear constraints, you're narrowing that probability distribution. You're steering the predictive engine exactly where you want it to end up.
Section 4. Solving problems with LLMs, real-world applications.
Let's pull this out of the abstract statistics for a second and look at a really practical use case. Imagine a startup team just drowning in social media comments, way too many for a human to read. They can use an LLM for automated sentiment analysis. By passing a social media post into the prompt, the LLM classifies the emotional tone of that raw text into predefined buckets, like positive, neutral, or negative. Now, the model isn't feeling the text. It's just recognizing that the token sequence for a phrase like "this crashes every time" strongly statistically correlates with the negative label based on all its training. This instantly lets the startup automatically bubble up those critical, angry posts straight to support for immediate help. That literally saves countless hours of manual triage.
But if you actually want to use that classification seamlessly inside your existing software architecture, getting a conversational text response back from the model is just not going to cut it. Your code can't easily parse conversational English. To make this efficient, you need the LLM to return structured output, specifically JSON. JSON is the lightweight data format we all use to easily transfer information. By passing the strict JSON schema into the SDK, you force the AI to return its answers in a perfectly structured, machine-readable format. This ensures your app can just instantly consume the response without you having to write a bunch of complex, super fragile text parsing logic. And the best part? It doesn't add overhead. It actually speeds up inference and drastically reduces the number of examples you have to shove into your prompt.
Section 5. Understanding model limitations. The safety warnings.
Okay, before you go wiring this all up in production, we absolutely need to map out the landmines. LLMs are incredibly powerful, yes, but they are not artificial general intelligence, and they have very real boundaries. First up, limited training knowledge. They have hard cutoff dates based on when they finished training, so out of the box, they don't know yesterday's news. Second, hallucinations. You have to remember the AI isn't querying some SQL database of verified, peer-reviewed facts. It's just calculating the next most likely word. If a plausible-sounding lie has a high statistical probability, it will confidently present it to you as absolute fact. Third, human bias. Because they learn from vast, unfiltered swaths of the internet, they absorb skewed data without any moral filter. And finally, multi-step reasoning. Because they generate text word by word rather than pausing to map out a comprehensive plan, they can easily lose the plot, skip steps, or completely mix up facts along the way.
There's also a very specific prompting limitation you're going to hit immediately, which is the lost in the middle effect. When you feed an LLM a massive document or a huge block of context, its attention mechanism really struggles. It heavily weighs the instructions at the very beginning of your prompt and the context at the very end, but it will frequently completely ignore crucial constraints or data buried right in the middle. It just becomes a total mystery to the model. Knowing this is a total game changer for prompt engineering. You always want to place your most critical instructions at the very end of your text, ensuring that statistical engine weighs them heavily right before it starts generating its output.
Section 6. Plugging LLMs into code, APIs and SDKs.
So, now that we know the rules of the road, how do we actually plug these tools into our apps? You've got a few options from AI providers. You could use raw REST APIs to make direct web calls, but honestly, doing that is like dealing with a huge tangled mess of extension cords. You have to manually handle every single connection timeout, write your own retry logic, manage messy HTTP headers, and manually parse raw JSON streams. It's just a ton of unnecessary boilerplate code. Instead, you want to use low-level SDKs. These are lightweight wrappers provided by companies like OpenAI or local hosters like Llama. An SDK packages all that messy connection logic into a clean, single, organized interface. You get maximum programmatic control over your configuration settings without the headache. For performance-critical workloads, this is hands down the best approach.
Section 7. Looking ahead. Building autonomous systems. Once you've really mastered bending LLMs to your will using SDKs and forcing structured JSON outputs, a whole new world of software architecture opens up. You move completely beyond basic chat interfaces and simple input-output workflows. You start building agentic AI systems. This means giving the AI secure pathways, often called tools, to interact with the real world. So instead of just summarizing some text, an agentic system might independently decide to write a SQL query, execute it against your local database, read the resulting data, and then automatically draft and email a summary report to your team. The agent is actually making decisions, coordinating external tools, and adjusting its behavior based on the responses it gets to autonomously complete multi-step goals. It's pretty incredible. The foundational mechanics of large language models are no longer a black box. You now understand the probabilistic engine, why you need structured data, and the limitations you have to engineer around. This paradigm shift has already happened, and it is completely reshaping our industry. So, the only question left for you as a developer is, how will you use this knowledge to fundamentally change the way you build software? Will you stay entirely in the deterministic past, writing rigid if-then statements, or are you ready to start building the autonomous, intelligent systems of the future? Definitely something to think deeply on as you start writing those first programmatic AI calls.